the proof of what we call the chain rule. I would like to greet you again. Welcome. This is Sipho, the equation killer. Welcome to our mathematical calculus. Today we're going to focus on what we call the proof of what we call the chain rule. So let's begin with our lesson without wasting any time. I said we're going to talk about what we call the chain rule. The chain rule. We want to talk about what we call the chain rule. So now, as far as we're concerned, oh, if our function f and our function g are differentiable, functions, then dx of our function f at x multiplied by our function g at x, this one becomes our f at x multiplied by the derivative of the second function, or you can even multiply with the first function. This one is up to you which one you go with, because it's a plus. G at x plus, then you copy the second one, you multiply by the derivative of the second one, which is our f at x. Or on this one, you can say you can multiply the first function, you can derive the first function and multiply by the first second function, you see the plus, then you copy the first function, then you multiply by the derivative of the second function. On this one, because it's plus, or it's up to you. So let's go for a proof on this one. Let's go with our proof. So now, we are going to prove so as far as we're concerned, we form the difference quotient, right? So we form the difference quotient, So our f at x plus h multiplied by our g at x plus h minus f at x multiplied by g at x divided by our h. So if we introduce our f at x plus h and g at x, so we can add it and subtract it at the same time. It means we are going to have our f at x plus h multiplied by our g at x plus h minus our f at x plus h multiplied by our g at x. Then we then add this. I know we subtract, we add so that they can cancel each other again. So it's like we didn't change anything on our equation, but there we were having minus f at x multiplied by g at x. So all of this is divided by our h. So if you can check here, those two, they can cancel each other. So it seems like there's nothing we have changed so far. So now, and we write it as, if we can separate, you can see that if we can separate this, we're going to have, I won't skip any step, we're going to have f at x plus h. We're going to have f at x plus h multiplied by g at x plus h minus our f at x plus h multiplied by g at x divided by h divided by h, then plus again, even the second one is also divided by our h. We're going to have something like this. If you can agree with me, we're going to have something like this. So on the first one, we can remove what we call the common factor, and our common factor is f at x plus h. So it means we're going to be left with what? With the g at x plus h minus g at x. So divided by h. And even on our second one, we have a common factor, which is nothing but our g at x. So this is g at x into, we're going to have our f at x plus h minus our g at x. No, minus our f at x, sorry about that. Minus our f at x because we took g at x as our common factor. So it's divided by h. So now, as far as we're concerned, let's continue with our equation. If you can check, you can agree with me that indeed, since f and g, since our f and g is differentiable at x. So we know that we know that f is continuous at x, and thus what? And thus when we are saying our limit, that's when we are saying our limit, of h approaches 0 of f at x plus h is nothing but equals to our f at x. That's where we are saying our limit of x, h approaching 0 of our f at x plus h is equals to f at x. So since we know that our g prime at x is nothing but equals to the limit of what? Of h approaching 0 of g at x plus h, remember, is same with the first principle, minus g at x, all divided by h. And we know that our f prime at x is nothing but equals to the limit of h approaching 0 of our f at x plus h minus our f at x, all divided by h. So on that one, it means we obtain it means we're going to obtain the limit of h approaching 0 of our f at x plus h, the limit of h approaching 0 of our g at x plus h minus g at x divided by h plus our g at x, the limit of h approaching 0 of our f at x plus h minus our f at x divided by h. So this one becomes what? We know that our limit of h approaches 0 of f at x plus h is what? Is nothing but what? It's nothing but our f at x. So now, as far as we are concerned, this one, it means is going to become, this is equals to our f at x multiplied by, we know that the limit of h approaches 0 of g at x plus h minus g at x over h is nothing but g prime at x, then plus g at x multiplied by this one give us f at x, which is the derivative. Or in this one, we can write it as, you can start by that one, then you multiply by this one, then you say the plus, you copy this one, then you multiply by this one. So it's the same things. So therefore we have proved that indeed the derivative of two functions multiplying each other, let's say f at x multiplied by g at x, we said is the same as we can derivate the first, then we copy the second, then we said plus, we copy the first, we derivate the second. That's all. Thank you very much for your time. Let's meet on the next session.